Hello students. So today's goal is to talk about logarithms and algebra. In particular, I want to identify 4 particular results which collectively are known as logarithm laws. So here they are. These items I will refer to as logarithm laws or just log laws. There's some algebraic rules which logarithms follow. The first one you already know. The first one says, well, what's the log of 1? Well, you know what the log of 1 is. If you want to, well, let's remind ourselves what the log of 1 is. If you want to know what the log base b of 1 is, well, if the log base b of 1 is something that you'd like to figure out, you can take that and you can rewrite it in exponential form. 1 is equal to b to the star. So this asks you what power of b is equal to 1. Well, that's easy. B to the 0 is equal to 1. So that means log base b of 1 is 0. The log of 1 is 0 no matter what base you're walking over. There's the first fact, and you notice that that was because b to the 0 is equal to 1. So the idea is logs and exponentials are so closely related. Logs are inverses of exponentials. So for every fact you know about logs, you know a fact about exponentials. And conversely, every fact about exponentials gives you a fact about logs. So we're going to fill these out as we get them. Let's start with this one. What do logs do to multiplication? What is the log of x times y? Well, let's try to figure it out. So here's the way that we'll structure this argument. So we want some formula that has to do with the log of x and the log of y. Presumably, if you know the log of x and the log of y, you can figure out what x and y are, so you can figure out what the log of x times y is. So let's start by giving a name to the log of x and the log of y. Let's call it the log of little x, I don't know, big X. Let's call the log of little y, big Y. Doesn't matter what you call them. But these two equations, they tell us something. It looks like I've just given something a name, but I know things about logarithms. So I can take that equation and rewrite it, instead of in logarithmic form, in exponential form. I'll be able to conclude that x is equal to b raised to the power big X. And maybe for emphasis, I'll put crosshairs on my x. And log base b of little y is equal to big Y, which there. Now it definitely looks different. So that means y is equal to b to the power big Y. Okay, so let's walk with that a little bit. I eventually want to understand what the log base b of x times y is. There's the thing that I want to know. Let's look at it, the inside. Let's try to compute x times y. That is b to the big X times b to the big Y, also known as b to the big X plus big Y, because of the exponential law that b to the x times b to the y is b to the x plus y. I did intentionally leave that empty to begin with, but now I'm filling it in now that I've used it. So let's think about what that means. I now have what x times y is. It's b to the big X plus big Y. So let's compute its log. The log of x times y is equal to the log base b of b to the x plus y. But remember, logs and exponentials are inverse functions. They'll cancel each other. So this and this will cancel, leaving me with just, big X plus big Y. And, well, big X and big Y were artificial things that I didn't actually care about. I cared about them because they had to do with log. Big X is log base b of x. Big Y is log base b of y. So our first main formula, which we've even now seen why it's true, says that the log with any base of x times y is equal to the log base b of x plus the log base b of y, little y. Cool. So let's think about, well, let's write it down up here first. So let's write down the other exponential laws, and then we'll get a guess as to what the resulting logarithmic laws will be. The quotient of exponentials, b to the x divided by b to the y, is b to the power x minus y. The exponential of an exponential of an exponential, is given by b to the x to the y is equal to b raised to the power x times y. So that should give some good intuition. The reason that logs turn multiplication into addition is because exponential does the opposite. If you see addition inside of the exponential, it becomes multiplication outside. I want to know what happens when you see division inside. Well, when you see division outside of an exponential, it turns into subtraction on the inside. So division on the inside of a log should become subtraction outside. Maybe that's being hopeful instead of rigorous, but we'll actually explain why later. And finally, and we will justify this rule also, the log base b of x to the power y is always equal to y times the log base b of x. So let's use these. And let's start by just using this rule. Let's use the fact that a sum of logs is the log of a product. The log of the product is the sum of the logs. So let's use that to try to compute this. So I see log base 3 of 2 plus the log base 3 of 1.5. 2 and 3, those are not powers of 2 and 1.5 are not powers of 3, so I can't make this computation directly. I need to do some tricks. So here's the trick. That's the log of a product. That's a sum of logs. The sum of two logs, according to this rule, there's a sum of two logs, is equal to the log of the product. So the log base 3 of 2 plus the log base 3 of 1.5 is equal to the log base 3 of 2 multiplied by 1.5. 2 times 1.5, I know what that is. That's the log base 3 of 3. And that's one of the few logs that's computable. 3 is a power of 3. 3 is 3 to the 1. So log base 3 of 3 is 1. Nice. So, box is the answer. Even though I didn't know what the log base 3 of 2 was, and I didn't know what the log base 3 of 1.5 is, because I knew logarithm laws, I could rewrite that sum as something that I do know. Logarithm laws are powerful because of that. They're also powerful because they give you a way of simplifying. If you see two logs added together, you can rewrite that as a single log, which is exactly what we did right there. But when you're solving an equation, if there's a single log on, say, the left-hand side of an equation, then you can undo it. You can rewrite an exponential form to get rid of the log. Let's see that in practice. Let's solve this equation. Log base 3 of x plus the log base 3 of x plus 8 is equal to 2. So here's how we'll do it. I see a log plus a log on the left-hand side. I can turn that into a single log of the product. So on the left-hand side, I actually see the log. Still the same base. None of these rules change the base. We will get a rule in a little bit by the end of this packet, which changes the base. The log basically of the product of the two things in the parentheses is equal to 8. Ah. There's an equation that's in log form. It's just a logarithm set equal to 2. So it's an equation in log form, so we can undo the log. We can rewrite it in exponential form, getting x times x plus 8 is equal to the base, 3 raised to the power 2, but fancy that, that's just 9. Simplifying, I get x squared plus 8x, right, that's just distributing the x on the left-hand side, subtract the 9 to the other side, minus 9 equals 0. Oh, so that's like a quadratic equation. That's easy to solve. Let's solve that quadratic equation, I guess by factoring first? Yeah, let's try factoring. So to factor this, I need two numbers which multiply together to be -9 and add together to be 8. Let's see, 9 and -1, those will do. Gives me x plus 9 times x minus 8. X minus 1 equals 0. And whenever you solve something by factoring, especially if you're feeling the way I am right now, that is a little bit loopy, you can check this by FOILing. X times x is x squared. First outside minus x. Inside plus 9x. Last minus 9. Yeah, that's x squared plus 8x minus 9. So, check that. That can stay. So, I see now two solutions to this. Apparently x is equal to -9, or x is equal to 1. Like -9 coming from this piece, x equals 1 coming from this piece. All right, well, let's go ahead and do a quick double check, and there's a reason that I want to do this double check. We'll see a particular thing happen. Let's plug in these x values and see if they actually solve the equation. So let's start by plugging in x equals 1. What do we get when we plug in x equals 1? We get log base 3 of 1 plus the log base 3 of 1 plus 8. Well, let's see. That bit's just 9, which happily is a power of 3, so it's easy to take its log. That gives me log base 3 of 1, which is 0, plus the log base 3 of 9. 9 is 3 squared, so that's 2. Yeah, that's 2. That works out. Let's try to plug in -9. So I'll get, looking at the original equation, log base 3 of -9 plus the log base 3 of -9 plus 8. Oh, but I see some stuff that's wrong. Am I allowed to see a negative? Sorry. I keep thinking that I should have like someone that I'm lecturing to who will answer my questions. I don't. You can't have a negative inside a log. The domain of log is 0 to infinity, excluding 0. So -9 is not in the domain. And -9 plus 8, that's -1, not in the domain. so something's gone wrong. Only x equals 1 is in the domain of the original problem. And basically the reason that something went wrong is if you look in that very first step, I replaced two individual numbers with their product. Two negative numbers can multiply together to be a positive. So there are some circumstances where this quantity won't be defined even though this quantity is defined. So after you finish solving an equation, you should check to see if your things are actually in the domain of consideration. So in this case, x equals 1 is the only solution. Same thing, but with division, and we already got a guess. It seems reasonable to expect that the log base b of x over y is the log base b of x minus the log base b of y. And, well, the reason for this fact is pretty similar to the reason that the same thing holds for multiplication. We'll translate everything in this formula over to exponential form. We'll translate back to log and we'll be done. So let's start by giving things names. Let's just set the log base b of x. Let's call that t. Let's call the log base b of y s. It doesn't matter what you call these things, but let's just give them a name. I can rewrite those in exponential form to get x equals b to the t. Right, that's just taking this equation and putting it in exponential form. You can similarly take this and put it in actual exponential form, getting y is equal to b to the power s. Substituting and simplifying, x is b to the t divided by y is b to the s, gives me b to the t minus s. So the log base b of x minus y is the log base b I guess I'm not really rewriting in log form. Let's rewrite it in log form. Let's actually follow the instructions. So I see x over y is equal to b to the t minus s. That's an equation in exponential form. I see this thing is equal to a base to a power. So I can rewrite that as log base b of the thing on the other side, log base b of x times x over y, is equal to t minus s. But I know what t and s are. Here's t. Here's s. T is the log base b of x, minus s is the log base b of y. So yeah, log base b of x over y is equal to the log base b of x minus the log base b of y. That verifies that that thing is true. This we can use to do something. Everything that we could do with multiplication, division is basically the same, so let's do it. Let's compute the log base 5 of 15 minus the log base 5 of 3. Well, I see two logs being subtracted. So logarithm laws tells me this should be the same thing as the log base 5 of 15 divided by 3. So that's the log base 5 of 5. 15 divided by 3 is 5. That's 1. So again, log laws let you rewrite complicated things with multiple logs, in terms of things with a single log. Sometimes that thing with a single log is easier to understand. Let's try to use the same philosophy to solve an equation. Let's solve log base 2 of x plus 2 minus log base 2 of x plus 1 is equal to 3. And again, this won't be so bad. I see two logs being subtracted. So that should tell me that the log base 2, well, this is subtraction, so it should become division. So log base 2 of x plus 2 log base 2 of x plus 2 divided by x plus 1 is equal to 3, there's an equation in logarithmic form. It's a single log is equal to a number. That's what it means to be an equation in logarithmic form. So I can write that as x plus 2 divided by x plus 1 is equal to 2 to the power 3. And be careful about things like 2 to the 3 as opposed to 3 to the 2. Is that actually the right thing? Well, this is the base, right? There's the base right here. When you translate from log to exponential form, the base is still the base. But now it's the base in an exponential thing instead of a logarithmic thing. So yeah, that's the thing to have. And 2 to the 3 is 2 times 2 times 2 is 8. Okay, so x plus 2 divided by x plus 1 is equal to 8. That's a rational equation. We've solved those. If this were in class, I would ask if you guys want me to solve it, but we're not in class, are we? So you can't answer me in time, because you can write, I want you to solve it or not in the comments, but it won't change anything. Anyway, solving, if you want to solve this equation, well, it's annoying that there's a denominator on this side. That division makes me unhappy. That doesn't have to be division, though. I can move this to the other side as multiplication. So I'll multiply x plus 1 to the other side. So x plus 2 is equal to 8 multiplied by x plus 1, also known as 8x plus 8. So x plus 2 is equal to 8x plus 8. I just want to solve this for x. Let's see what we need to do that. So I guess let's subtract x to the other side, leaving me with 7x on the right-hand side. I'll subtract 8 from the right-hand side and the left-hand side, leaving me with negative 6. So we wind up with negative 6 over 7 equals x. And as we've kind of seen, whenever a negative shows up inside of a log, you should ask yourself, well, is this actually in the domain? And, well, we should ask ourselves that. Let's check. Domain check. In fact, you know what, let's actually just do a full-blown check if this solves the equation. Let's plug in x equal to negative 6 over 7 and see what we get. Well, we need to compute the log base 2 of negative 6 over 7 plus 1 minus log base 2 of negative 6 over 7 plus 1. Sorry, I think I may have said 1, but then I wrote 2. So let's just try to compute what that is. Keep the log base 2 around. So to simplify this, write 2 as 14 over 7. To simplify this, write 1 as 7 over 7. Continuing to simplify. Let's see. Common denominator. Makes it easy to add. I just have 14 minus 7 in the numerator, that's 8. Minus. Let's see. This is the same as 7 over 7 minus 6 over 7. 7 sevenths minus 6 sevenths leaves you with 1 7th. Okay, nice. So, one upshot is both of the things inside of those parentheses are positive. So this actually is a thing that exists. But I see a log minus a log. So this will become log base 2 of 8 over 7 divided by 1 over 7. And, well, there are two ways you could see to go from here. You could say, well, there's division in the denominator. Screw it. Let's just pick that one. There's division in the denominator. So that means instead of dividing by a fraction, I should multiply by the reciprocal. Those cancel, leaving me with the log base 2 of 8. Oh, but 8's a power of 2. 8 is 2 to the 3. So log base 2 of 8, that asks, what power do I need to raise 2 to in order to get 8? The answer is 3. Is that what I needed it to be? It is. Good. So x equals negative 6/7 is the solution. Nice. So logarithms change multiplication to addition. They change subtraction. They change division to subtraction. So both of those are like demotion. Multiplication is like souped up addition. Division is like souped up subtraction. Maybe that is less reasonable. Yeah, just stick with the multiplication. So that somehow should mean exponentiation should become a demoted form of exponentiation. Well, but exponentiation, that's like souped up multiplication. So the log of an exponential, I claim, will just be multiplication. Log base b of x to the y is y times the log base b of x. And let's try to see why. So the log base b of x, let's give it a name. Let's call it, oh goodness, star. No, I can't draw a star consistently on a tablet. Let's call it heart. It doesn't matter what you call a variable. I won't do anything with y. So there's an equation in log form. I can rewrite it in exponential form. I can rewrite this as x is equal to b raised to the power heart. So let's take the thing inside of the log that we're interested in. I'm eventually interested in log base b of x to the y. Let's write down what x to the y is if I know that x is b to the heart. So x to the y is b to the heart to the y. But I know exponential as that's b raised to the heart times y. So just writing that again, x is equal to b to the heart times y. That's an equation in exponential form. I can rewrite it in log form. Sorry, I lost the x, I lost the y. So this is an equation in exponential form with base b. I could also think of it as having base x, but I'll think of it as having base b. I can move the b to the other side as a base of a logarithm. And what do I get? I get the log base b of the left-hand side, x to the y, is equal to heart times y. But what is heart? Heart is the log base b of x. So that means that the log base b of x is equal, the log base b of x to the y is equal to the log base b of x times y. That was the last of those logarithm laws. So the remaining thing to do is, well, there's one other result that I have in here, but I think that's going to be in the second part of this video. Let's use the results we've gotten so far to solve one more equation. Let's solve 2 times the log base 5 of x plus 1 minus the log base 5 of x minus 1 is equal to 2. So the first thing that I see in this, let's zoom in. I want to solve that. I see a number times a logarithm. A number times a log, by this rule, whenever I see a number times a logarithm, I can move that number into the exponent inside of the log. So 2 times the log base 5 of x plus 1, that's exactly the log base 5 of x plus 1 squared. And the rest I'll just leave alone. Now I see a log minus a log. So let's deal with this subtraction sign. That's the difference between two logarithms. I can move that inside of the parentheses, have a single log, and have subtraction. Leaving me with the log base 5 of x plus 1 squared. Blue subtraction will become blue division, just for emphasis. Divide by x minus 1 equals 2. Now I see an equation that's in logarithmic form. I should rewrite that equation in exponential form. Oh, nice. And now what do I see? I see a rational equation. I see finger slipped. I see a rational function on the left-hand side is equal to 25. So I have a plan, right? I should turn that into a polynomial equation. How do you turn a rational thing into a polynomial thing? Well, you clear the denominators. So let's clear the denominators on the left-hand side of that by multiplying both sides by x minus 1. And maybe I'll FOIL out the x plus 1 squared. X squared plus 2x plus 1 is equal to, multiply x minus 1 to the other side, 25x minus 25. And, I mean, it's mechanical now. Subtract 25x to the other side, add 25 to both sides. Wind up with x squared minus 25. So 2 minus 25, that's minus 23x. Add 25 to the other side, plus 26 equals 0. Those numbers are big enough that I'm not going to try to factor it. There's no way that it will walk out. Maybe I shouldn't be such a naysayer, but I don't think it'll walk out. Let's use the quadratic formula. I'll end up with solutions of the form x equal to negative b plus or minus the square root of b squared minus 4 times a times c, 26, all over 2. And I want to check, at least informally, to see if these things are actually in the domain. So let's look at the original function and try to determine what the domain is. So these two things inside of the parentheses have to be positive. X plus 1 has to be positive. X minus 1 has to be positive. So x has to be bigger than negative 1. X has to be bigger than 1. This is the stronger of the two conditions. So I'll just make sure that x is bigger than 1. And maybe it's not so easy to see whether this quantity, how it compares with 1. I guess in the choice of the plus branch, I have two choices. In the plus choice, it's obviously bigger than 1, because 23 divided by 2 will already be like 11 and some change, way bigger than 1. And I'm making it bigger, I'm adding. In the minus choice, it's less clear. In order to decide, I think here's how I'll do that. Put that in a place so I can still see it. But sorry, you don't necessarily need to watch me type. I'll be back. Alright, so there's one of the two things that we want to compute. Well, maybe it's nice to actually get it in pretty print. Yeah, so 1/2, 23 plus the square root of all that stuff is around 21.8. Which is clearly in the domain. And the other one is somewhere around 1.2. Cool. So, getting rid of this. As we decided, x has to be bigger than 1 for everything to make sense. And both of those are bigger than 1. Both solve the equation. So the next thing to happen in these notes will be thinking about the change of basis formula. So that's a big enough idea that I think it shouldn't go at the end of the video. We went at the end of a lecture because that's where it fit in terms of hour-long things, but I don't need to compose hour-long things. So I'll stop this where it is, and I'll see you later with, the change of basis formula for logarithm laws. Keep on going.